RAID is a data storage virtualization technology that combines multiple disk drive components into a logical unit for the purposes of data redundancy or performance improvement. Data is distributed across the drives in one of several ways, referred to as RAID levels, depending on the specific level of redundancy and performance required. The different schemes or architectures are named by the word RAID followed by a number. Each scheme provides a different balance between the key goals: reliability and availability, performance and capacity. RAID levels greater than Reader 0 provide protection against unrecoverable read errors, as well as whole disk failure. History: the term RAID was invented by David Patterson, Garth A. Gibson, and Randy Katz at the University of California, Berkeley in 1987. They studied the possibility of using two or more hard disk drives to appear as a single device to the host system and published a paper titled A Case for Redundant Arrays of Inexpensive Disks in June 1988 at the SIGMOD conference. Each of the 5 levels of RAID named in the paper were well established in the art prior to the paper's publications. For example, around 1983, DEC began shipping subsystem mirrored RA8X disk drives as part of its HSC50 subsystem. Around 1988, the Thinking Machines Data Vault used error correction codes in an array of disk drives. A similar approach was used in 1970s on the IBM 3330. In 1977, Norman Kenauchi at IBM filed a patent disclosing what was subsequently named Reader 4. In 1986, Clark A. al. at IBM filed a patent disclosing what was subsequently named Reader 5. Industry RAID manufacturers later tended to interpret the acronym as standing for Redundant Array of Independent Disks. Concept: many RAID levels employ an error protection scheme called parity, a widely used method in information technology to provide fault tolerance in a given set of data. Most use simple XOR, but Reader 6 uses 2 separate parities based respectively on addition and multiplication in a particular Gaulois field or Reader Euro-Solomon error correction. Standard levels. A number of standard schemes have evolved. These are called levels. Originally, there were 5 RAID levels, but many variations have evolved Euro, notably several nested levels and many non-standard levels. RAID levels and their associated data formats are standardized by the Storage Networking Industry Association in the Common RAID Disk Drive Format Standard, RAID 0. RAID 0 comprises striping. This level provides no data redundancy nor fault tolerance, but improves performance through parallelism of read and write operations across multiple drives. Reader 0 has no error detection mechanism, so the failure of one disk causes the loss of all data on the array. RAID 1. RAID 1 comprises mirroring. Data is written identically to 2 drives, thereby producing a mirrored set. The read request is serviced by any of the drives containing the requested data. This can improve performance if data is read from the disk with the least seek latency and rotational latency. Conversely, write performance can be degraded because all drives must be updated. Thus the write performance is determined by the slowest drive. The array continues to operate as long as at least one drive is functioning. RAID 2. RAID 2 comprises bit-level striping with dedicated Hamming code parity. All disk spindle rotation is synchronized and data is striped such that each sequential bit is on a different drive. Hamming code parity is calculated across corresponding bits and stored on at least one parity drive. This level is of historical significance only. Although it was used on some early machines, it is only recently used by high-performance commercially available systems. RAID 3. RAID 3 comprises byte-level striping with dedicated parity. All disk spindle rotation is synchronized and data is striped such that each sequential byte is on a different drive. Parity is calculated across corresponding bytes and stored on a dedicated parity drive. Although implementations exist, Reader 3 is not commonly used in practice. RAID 4. RAID 4 comprises block-level striping with dedicated parity. This level was previously used by NetApp, but has now been largely replaced by a proprietary implementation of Reader 4 with 2 parity disks, called RAID DP. RAID 5. RAID 5 comprises block-level striping with distributed parity. Unlike in RAID 4, parity information is distributed among the drives. It requires that all drives but one be present to operate. Upon failure of a single drive, subsequent reads can be calculated from the distributed parity such that no data is lost. Reader 5 requires at least 3 disks. RAID 5 is seriously affected by the general trends regarding array rebuild time and chance of failure during rebuild. In August 2012, Dell posted an advisory against the use of Reader 5 in any configuration and of Reader 50 with Class 2 7200 RPM drives of 1 TB and higher capacity. RAID 6 comprises block-level striping with double distributed parity. Double parity provides fault tolerance up to 2 failed drives. This makes larger RAID groups more practical, especially for high availability systems, as large capacity drives take longer to restore. As with Reader 5, a single drive failure results in reduced performance of the entire array until the failed drive has been replaced. With a Reader 6 array, using drives from multiple sources and manufacturers, it is possible to mitigate most of the problems associated with Reader 5. The larger the drive capacities and the larger the array size, the more important it becomes to choose Reader 6 instead of Reader 5. Reader 10 also minimizes these problems. Nested RAID. In what was originally termed hybrid RAID, many storage controllers allow RAID levels to be nested. The elements of a RAID may be either individual drives or arrays themselves. Arrays are rarely nested more than one level deep. The final array is known as the top array. When the top array is Reader 0, most vendors omit the plus. Reader 0 plus 1 creates a second striped set to mirror a primary striped set. The array continues to operate with one or more drives failed in the same mirror set, but if drives fail on both sides of the mirror, the data on the RAID system is lost. Reader 1 plus 0 creates a striped set from a series of mirrored drives. The array can sustain multiple drive losses so long as no mirror loses all its drives. Non-standard levels. Many configurations other than the basic numbered RAID levels are possible, and many companies, organizations, and groups have created their own non-standard configurations, in many cases designed to meet the specialized needs of a small niche group. Such configurations include the following. Linux MD RAID 10 provides a general RAID driver that in its near layout defaults to a standard Reader 1 with 2 drives, and a standard Reader 1 plus 0 with 4 drives. Though, it can include any number of drives, including odd numbers. With its file layout, MD Reader 10 can run both striped and mirrored, even with only 2 drives in F2 layout. This runs mirroring with striped reads, giving the read performance of Reader 0. Regular Reader 1, as provided by Linux software RAID, does not stripe reads, but can perform reads in parallel. Hadoop has a RAID system that generates a parity file by storing a stripe of blocks in a single HDFS file. Implementations. The distribution of data across multiple drives can be managed either by dedicated computer hardware or by software. A software solution may be part of the operating system, or it may be part of the firmware and drive is supplied with the hardware RAID controller. Software-based, software RAID implementations are now provided by many operating systems. Software RAID can be implemented as a layer that abstracts multiple devices, thereby providing a single virtual device, a more generic logical volume manager, a component of the file system. Some advanced file systems are designed to organize data across multiple storage devices directly. ZFS supports equivalents of Reader 0, Reader 1, Reader 5, Reader 6 and a triple parity version Reader Z3. As it always stripes over top-level VDEVS, it supports equivalents of the 1 plus 0, 5 plus 0, and 6 plus 0 nested RAID levels but not other nested combinations. ZFS is the native file system on Solaris and also available on FreeBSD and Linux. BTRFS supports Reader 0, Reader 1 and Reader 10. Many operating systems provide basic RAID functionality independently of volume management. Apple's OS X and OS X Server support Reader 0, Reader 1, and Reader 1 plus 0. FreeBSD supports Reader 0, Reader 1, Reader 3, and Reader 5, and all nestings via GEOM modules and CCD. Linux's MD supports Reader 0, Reader 1, Reader 4, Reader 5, Reader 6, and all nestings. Certain reshape and expanding operations are also supported. Microsoft Server operating systems support Reader 0, Reader 1, and Reader 5. Some of the Microsoft desktop operating systems support RAID. For example, Windows XP Professional supports RAID Level 0, in addition to spanning multiple drives, but only if using dynamic disks and volumes. Windows XP can be modified to support Reader 0, 1, and 5. Windows 8 and Windows Server 2012 introduces a RAID-like feature known as storage spaces, which also allows users to specify mirroring, parity, or no redundancy on a folder-by-folder basis. NetBSD supports Reader 0, 1, 4, and 5 via its software implementation, named RAIDframe. If a boot drive fails, the system has to be sophisticated enough to be able to boot off the remaining drive or drives. For instance, consider a computer whose disk is configured as Reader 1. If the first drive in the array fails, then a first-stage bootloader might not be sophisticated enough to attempt loading the second-stage bootloader from the second drive as a fallback. The second-stage bootloader for FreeBSD is capable of loading a kernel from such an array. Firmware driver-based. Software-implemented RAID is not always compatible with the system's boot process, and it is generally impractical for desktop versions of Windows. However, hardware RAID controllers are expensive and proprietary. To fill this gap, cheap RAID controllers were introduced that do not contain a dedicated RAID controller chip, but simply a standard drive controller chip with proprietary firmware and drivers. During early-stage boot-up, the RAID is implemented by the firmware, and once the operating system has been more completely loaded, then the drivers take over control. Consequently, such controllers may not work when driver support is not available for the host operating system. An example is Intel Matrix RAID, implemented on many consumer-level motherboards. Because there is some minimal hardware support involved, this implementation approach is also called hardware-assisted software RAID, hybrid model RAID, or even fake RAID. If Reader 5 is supported, the hardware may provide a hardware XOR accelerator. An advantage of this model over the pure software RAID is that if using a redundancy mode the boot drive is protected from failure during the boot process even before the operating system's drivers take over. Uses: RAID can provide data security with solid-state drives without the expense of an all-SSD system. For example, a fast SSD can be mirrored with a mechanical drive. For this configuration to provide a significant speed advantage, an appropriate controller is needed that uses the fast SSD for all read operations. ADAPT calls this hybrid RAID. Integrity: data scrubbing involves periodic reading and checking by the RAID controller of all the blocks in an array, including those not otherwise accessed. This detects bad blocks before use. Data scrubbing checks for bad blocks on each storage device in an array, but also uses the redundancy of the array to recover bad blocks on a single drive and to reassign the recovered data to spare blocks elsewhere on the drive. Frequently, a RAID controller is configured to drop a component drive if the drive has been unresponsive for 8 seconds or so. This might cause the array controller to drop a good drive because that drive has not been given enough time to complete its internal error recovery procedure. Consequently, using RAID for consumer-marketed drives can be risky, and so-called enterprise-class drives limit this error recovery time to reduce risk. Western Digital's desktop drives used to have a specific fix. A utility called WDTLERX limited a drive's error recovery time. The utility enabled TLER, which limits the error recovery time to 7 seconds. Around September 2009, Western Digital disabled this feature in their desktop drives, making such drives unsuitable for use in RAID configurations. However, Western Digital Enterprise-class drives are shipped from the factory with TLER enabled. Similar technologies are used by Seagate, Samsung, and Hitachi. Of course, For non-RAID usage, an enterprise-class drive with a short error recovery timeout that cannot be changed is therefore less suitable than a desktop drive. In late 2010, the SmartMon Tools program began supporting the configuration of ATA error recovery control, allowing the tool to configure many desktop-class hard drives for use in RAID setups. While RAID may protect against physical drive failure, the data is still exposed to operator, software, hardware, and virus destruction. Many studies cite operator fault as the most common source of malfunction, such as a server operator replacing the incorrect drive in a faulty RAID, and disabling the system in the process. An array can be overwhelmed by catastrophic failure that exceeds its recovery capacity and, of course, the entire array is at risk of physical damage by fire, natural disaster, and human forces, while backups can be stored off-site. An array is also vulnerable to controller failure because it is not always possible to migrate it to a new, different controller without data loss. Weaknesses, correlated failures. In practice, the drives are often the same age and subject to the same environment. Since many drive failures are due to mechanical issues, this violates the assumptions of independent, identical rate of failure amongst drives. Failures are in fact statistically correlated. In practice, the chances of a second failure before the first has been recovered is higher than for random failures. In a study of about 100,000 drives, the probability of two drives in the same cluster failing within 1 hour was 4 times larger than predicted by the exponential statistical distribution Euro, which characterizes processes in which events occur continuously and independently at a constant average rate. The probability of 2 failures in the same 10-hour period was twice as large as predicted by an exponential distribution. Unrecoverable read errors during rebuild. Unrecoverable read errors present as sector read failures. The unrecoverable bit error rate is typically specified at 1 bit in 1015 for enterprise-class drives, and 1 bit in 1014 for desktop-class drives. Increasing drive capacities and large reader 5 redundancy groups have led to an increasing inability to successfully rebuild a RAID group after a drive failure because an unrecoverable sector is found on the remaining drives. Parity schemes such as Reader 5 when rebuilding are particularly prone to the effects of UREs as they affect not only the sector where they occur but also reconstructed blocks using that sector for parity computation. Typically an URE during a Reader 5 rebuild leads to a complete rebuild failure. Double protection schemes such as Reader 6 are attempting to address this issue, but suffer from a very high write penalty. Schemes that duplicate data such as REDSA 1 and 10 have a lower risk from UREs than those using parity computation. Background scrubbing can be used to detect and recover from UREs as a background process, by reconstruction from the redundant RAID data and then rewriting and remapping to a new sector. And so reduce the risk of double failures to the RAID system. Increasing rebuild time and failure probability. Drive capacity has grown at a much faster rate than transfer speed, and error rates have only fallen a little in comparison. Therefore, larger capacity drives may take hours, if not days, to rebuild. The rebuild time is also limited if the entire array is still in operation at reduced capacity. Given an array with only one drive of redundancy, a second failure would cause complete failure of the array. Even though individual drives' mean time between failure have increased over time, this increase has not kept pace with the increased storage capacity of the drives. The time to rebuild the array after a single drive failure, as well as the chance of a second failure during a rebuild, have increased over time. Some commentators have declared that Reader 6 is only a band-aid in this respect, because it only pushes the problem a little further down the road. However, according to a 2006 NetApp study of Berryman al., the chance of failure decreases by a factor of about 3,800 for a proper implementation of Reader 6, even when using commodity drives. Nevertheless, if the currently observed technology trends remain unchanged, in 2019 a Reader 6 array will have the same chance of failure as its Reader 5 counterpart had in 2010. Mirroring schemes such as Reader 10 have a bounded recovery time as they require the copy of a single failed drive, compared with parity schemes such as Reader 6, which require the copy of all blocks of the drives in an array set. Triple parity schemes. or triple mirroring, have been suggested as one approach to improve resilience to an additional drive failure during this large rebuild time. Atomicity, including parity inconsistency due to system crashes. A system crash or other interruption of a write operation can result in states where the parity is inconsistent with the data due to non-atomicity of the write process, such that the parity cannot be used for recovery in the case of a disk failure. The RAID write hole is a known data corruption issue in older and low-end RAIDs, caused by interrupted destaging of writes to disk. This is a little understood and rarely mentioned failure mode for redundant storage systems that do not utilize transactional features. Database researcher Jim Gray wrote Update in Place is a poison apple during the early days of relational database commercialization. Write cache reliability. A concern about write cache reliability exists, specifically regarding devices equipped with a write-back cookie a caching system that reports the data as written as soon as it is written to cache, as opposed to the non-volatile medium. See also, network-attached storage, non-RAID drive architectures, redundant array of independent memory, references. External links, RAID at DMOZ, Empirical Measurements of Disk Failure Rates and Error Rates, by Jim Gray and Catherine Van Ingen, December 2005, The Mathematics of RAID 6, by H. Peter Anvin, Does Fake RAID Offer Any Advantage Over Software RAID? A Euro discussion on superuser.com, Differences between Hardware RAID, HBAs, and Software RAID a Euroservethehome.com, Anatomy of a Hardware RAID Controller a Euroservethehome.com, Comparing RAID Implementation Methods a Eurodell.com, BAARF, Battle Against Any RAID 5, How Does RAID 5 Work? Easy explanation of RAID 5.